All right, so we're going to set the stage by considering or introducing the concept of first integrals, which are basically objects which are conserved. It's like by the flow of a dynamical system. All right, so let's say that you are given a differential equation. Let's say y dot is equal to f of y, and where y is a vector, or possibly a matrix. Okay, so I'm going to introduce this idea of a first integral. Okay, so you have a non-constant function. Let's say I of y is called a first integral of the differential equation if the following is true. Okay, which is that if you differentiate I and you multiply it by the vector field, this is 0 for all y. Okay, so another way to think about this is that the directional derivative of I, it's like in the direction of the flow, is 0. Okay, and the implication of a condition like this is that every solution of the differential equation has the following property. So this implies that every solution y of t of the differential equation, okay, satisfies the property that if you evaluate this function I on these solution curves, then this function is constant along those solution curves. Again, it's like this is not to say that I is a constant function. The assumption is that I is not constant, otherwise obviously a condition like this would trivially hold. So you're looking for functions which are not constant functions on the entire domain, but happen to be constant when restricted to a solution curve of the differential equation. Okay? So in addition to referring to these things as first integrals, they are oftentimes referred to as invariants, conserved quantities, or constants of motion. So invariant, conserved quantity, okay, or constants of motion. All right, okay, so perhaps it's worthwhile then to look at a few examples of such first integrals just to make this concept a little bit more concrete. So let's consider the Lotka-Volterra equation. So this is a predator-prey model. It's like which arises, for example, in mathematical biology. Okay, so it consists of this sort of coupled system of differential equations. Okay, so this is for the predator, and then this is for the prey. And they're part of a more general class of sort of models of the form u dot is au minus b uv, and v dot is equal to minus c plus d uv. Okay, and so this specific one just comes from specific choices of parameters a, b, c, and d. So here a is minus 2, b is minus 1, c is minus 1, and d is minus 1. Okay, so this is the more general, it's like class of models. Okay, and then you can check that if you have, again, it's like one of these models, it's like there is a first integral, which is again non-constant, but whose directional derivative along the vector field vanishes. Okay, so this has a first integral. Of the form I, which depends on u and v, which is the natural log of u minus u plus 2 times the natural log of v minus v. Okay, so this is for the specific case which we talked about. And then for the more general model, the first integral looks like the following. C natural log of u minus du plus a natural log of v minus bv. Okay, so again, then it's a relatively simple task to verify that when you differentiate I and you multiply it by the vector field, right, for u dot and v dot, right, that this thing vanishes. Okay, all right, so that's one example. Another class of examples, it's like which we're going to look at quite a bit more carefully in this class are examples of what are called Hamiltonian systems. So these are, analytical mechanical models for mechanical systems, and there are a whole bunch of very nice geometric properties. But for now, let's look at a relatively simple example, which is the pendulum. Okay, so the idea then is to look at the pendulum as what is called a Hamiltonian system. Okay, so there are what are known as Hamilton's equations. And they're defined in terms of a Hamiltonian H, which generally is a scalar-valued function on what is called the cotangent bundle of a configuration manifold. Okay, so Q is a configuration manifold. T star of Q is what is called the cotangent bundle. And in local coordinates, you typically have a position Q in the configuration manifold, and you have position and momentum variables on the cotangent bundle. Okay, all right. So given that setup, then given this scalar valued function on the cotangent bundle, then Hamilton's equations looks like the following. Q dot is equal to dh dp and P dot is equal to minus dH dq. Okay, so if you want to be a little bit more precise about this, this is the equations you get. It's like if you have a canonical symplectic structure. So this is for a canonical symplectic structure. And if you haven't sort of seen this before, it's like let's not worry about it for too much. But you know, it's like the usual form of Hamilton's equations, or the canonical form of Hamilton's equations, is written in this way. Okay, so let's now try to frame the planar pendulum and view this as a Hamiltonian system. So the planar pendulum. Okay, and to make life easier, it's like I'm going to normalize. It's like a few of the parameters. So I'm going to let the mass be 1, the length be 1, and gravity be 1. So I'm just going to choose appropriate units. It's like so all these things scale out, if you will. So if you have that, then the Hamiltonian for the planar pendulum looks like the following. So it's just 1/2 momentum squared minus cosine of q. Okay, so so perhaps it's worthwhile to say a little bit about what P and Q is. Okay, so let's draw a picture of this. So if you imagine that's the ceiling, for example, then you have a fixed point to the pendulum, and Q then is a generalized coordinate, which just corresponds to the angle the pendulum makes with the vertical direction of gravity. Okay, and then L is obviously the length of the pendulum, M is the mass, and then there is gravity acting on this, which is mass times gravity. Okay, and then this length here is just L times cosine of Q. Okay, all right. So the way to sort of think about this is that this is a kinetic energy term, and then this is a potential energy term having to do with the fact that there's a mass in a gravitational well. Okay. So if you have this Hamiltonian, then you can write down the corresponding equations of motion by substituting H into these canonical Hamilton's equations. So the equations of motion given by just Q dot is equal to P, okay, and then P dot is equal to minus sine of Q. All right, and of course, if you wanted to eliminate the momentum variable, then what you get is that P dot is equal to Q dot differentiated, right, which is equal to minus sine of Q. So this is telling you that the second derivative of Q is equal to minus sine of Q. Okay, so you can eliminate, it's like a momentum variable if you wish. It's like to get the more standard second order form of the equation. It's like just in terms of the position variables. Okay. So one thing it's like you'll find is that in general, it's like if you have a Hamiltonian system, as long as the Hamiltonian is independent of time, well, put another way, the only dependence of the Hamiltonian on time is like comes from the time dependence of the position of momentum, but there's no explicit time dependence, then there is a conserved quantity, which is the Hamiltonian itself. So let's try to see that. So the claim is that if H has no explicit time dependence, then it is a first integral of Hamilton's equations. Okay, so let's look at that. So if you take the time derivative of the Hamiltonian along a solution curve, of the differential equation, right, then by definition you get dH dq q dot plus dH dp p dot. Then you can substitute Hamilton's equations into this. So you get dH dq, and q dot is dH dp plus dH dp. Then p dot is minus dH dq. All right, and so it's sort of fairly clear that those two terms cancel. And this is telling you, again, that the Hamiltonian is a constant. It's like along solution curves of Hamilton's equations. All right, so let me just stop here for a minute.